hello once again. Welcome to the master series, meet the master session today. So please come in and be seated. Yeah, we are about to begin. Great. Okay, dear distinguished guests and participants of the 18th World Conference on Earthquake Engineering, welcome to the Meet the Masters event this afternoon. Implemented as part of the CSI IAEE Master Series, which is generously sponsored by Computers and Structures Incorporation. The Master Series of this 18th WCEE features 4 masters for read, meet, and greet the masters. Among the 4 masters today, I'd like to invite Professor Michele Calvi, Italy, for the Meet the Masters lecture. So Professor Michele Calvi has written a monograph entitled The Art of Seismic Design from Forces to Displacement Losses. This monograph is his own narrative about concept, various philosophies and methodologies, and their evolution towards the establishment of a rational approach for seismic design and the resilience of various structures. By the way, I'm Masayoshi Nakashima, serving as the immediate past president of IAEE. But anyway, here is a short introduction of Professor Calvi's professional work. What I learned from his monograph was, he was born in Italy and completed his undergraduate studies in Italy, obtained his Master of Science from the University of California at Berkeley, the United States of America, and his doctoral degree from the Politecnico di Milano, Italia. So Professor Calvi is the founder and the director of the Graduate School of Earthquake Engineering, nowadays called Road School, IUSS Pavia. He has received numerous honors and awards and has published research papers and textbooks of notable significance. Through his extensive interactions with many researchers and practitioners worldwide, he has played a significant role in strengthening international collaboration in our earthquake engineering community. Professor Calvi's contribution to the IAEE is also notable, with his service as IAEE's director between 2012 and 2021, and also IAEE's executive vice president from 2021 to today. So in retrospect, I met Michele for the first time in Milano and Pavia in 1986, 4 decades ago. There I met with a person called Giorgio Macchi, the legendary professor in Italy, and then we took a photo together, and I'm supposed to show the photo, but because of some mistakes, it didn't show up, but that's all right. Now, also Michele was very kind to invite me to Pavia University as a visiting professor, and also he appointed me as one of the founding members of the Road School and so forth. I had several opportunities, spend time in Pavia and interact with the students in Pavia and many young people from many places around the world. Now, I trust that many of you who are here have known Professor Calvi. Many of you have known Professor Calvi as a great researcher and who promotes performance-based engineering, as evidenced by his monograph and lecture today. Many of you also have known Professor Calvi as a prominent and successful practitioner who has accomplished many challenging civil engineering projects worldwide. And many of you, including myself, have known Professor Calvi as a great educator who has led the establishment of noble higher education systems such as Road School and IUSS. I genuinely admire my dear friend Michele for his unprecedented contributions to research, practice, and education of earthquake engineering altogether. So with this much of introduction, I'd like to invite my dear friends of 40 years, Michele Calvi, to the podium for his lecture. Your time.
It's a bit embarrassing to start this talk now. This story started more than 4 years ago when, together with a group of friends, we decided to try to apply for hosting the next World Conference. And this was the last clip, the last image of a video that we used to convince voters that that would have been a good choice. At that time, I was starting writing a book. Actually, I had already started. And when Farzad Naim and Masayoshi Nakashima asked me to write one of the monographs, I simply decided to quit the book and to use the material for the monograph. So it was much easier to me. The first thing that I would like to underline is that the title of this monograph has been originated by a sentence by Tsuneo Katayama at the World Conference in Vancouver 20 years ago, where he was underlining that seismic disaster mitigation, earthquake engineering if you want, is more an art than a skill, or skill rather than a science. He would say art of navigation, would not say science of navigation. He was underlining that in this area where we are all working, there is a combination of intelligence, creativity, science, but there is also a contribution coming from experience, which is fundamental. That's why I decided to entitle this monograph, The Art of Seismic Design. So it's a tribute to a person. And I will try to entirely talk about persons in the next 45 or 50 minutes. I think that in a short talk like this is the only way to try to transmit something. It's difficult to transmit an equation. It's easier to transmit some feeling, some emotional feeling, some perception about persons. When I was starting writing this book, I started wondering why I should write a book. And I recognized that there are books that I cannot try to match. One of these books, which is a book that I have always admired, is the Element by Euclid, written 300 years before Christ, that you all know that it starts with a point is that of which there is no part. This is something I would never be able to match. This is exclusive ground from geniuses. I'm not. Another kind of books is the kind of books like the Pliny's Naturalis Historia, which was written in the 1st century, or the Encyclopédie, written in the 18th century. But these kind of books are not useful anymore because they've been outdated by the web. Even if the web has not the same dependability, has not the same, you cannot trust the web as you could have been trusting the Encyclopédie by Diderot d'Alembert. So I was wondering why I should write a book and how. And unfortunately, or fortunately, in that days I was reading some story written by Jorge Luis Borges. And the point is that in one of his books, it is stated that nobody can really write a book. Because a book, to be really a book, needs dawns, sunsets, centuries, weapons, and the sea that is putting together and separating. Unfortunately, there is nothing of these sort of things in what I wrote, with maybe the exception of centuries. So I will now go not through the book, but through a tale where I will pick up some people that I consider I consider extraordinary people, and I will try to remind you of some of their visions and of some of their human obsessions. So, subjects, but always through some vision of the past. First subject I want to talk, performances and limit states. And the person I want to remind you is Julio Ferri Borges. Julio Ferri Borges was from Portugal, and in the early 70s, he was the chairman of the Joint Committee on Structural Safety. If you go back and read what they wrote more than 50 years ago, you'll be surprised how smart and close to visions of today are some of the sentences that they stated. And please consider that this was not focusing on earthquakes. So I think, well, I know there are too many words in this slide, but I think it was useful to put these words. Because what he states here is that the aim of risk management consists in increasing the benefit and reducing the loss. This was more than 50 years ago. And the strategies may be eliminating or avoiding the possible occurrence of the hazard, or avoiding the hazard acting in the system, or controlling or reducing the losses, or adopting a design which corresponds to a sufficiently small risk. I understand that this sounds like theory. Look at the next list of points. For example, if the hazard is the possible collapse of a column because of an impact of a car, then you can prevent car from approaching the building, which is the first point of the previous slide. Or you can install a protection for the column that would present the impact. Or you create a bracing system to avoid the collapse of the building if the column fails. Or you can design a sufficiently robust columns with a small probability of failure or impact. Or you can accept the column to fail, but you may avoid to have significant consequences. This is 50 years ago and not dealing with the earthquake, but for me was already something with the feeling of a prophecy. Today, when we talk about limit states, we have different views and feelings. I don't want to spend too much time on a slide like this where you are familiar. I'm simply representing spectral shapes using the well-known representation in terms of spectral acceleration, spectral displacement. But if you then represent structures with a kind of a pushover response, you will immediately realize that a structure that is fine for a frequent ground motion may not be fine for a rare ground motion. So let me pass to another subject. The other subject is force-based design. Those who are familiar with my talk know that I like to talk about all times, and I'm fully convinced that the essence of at least linear response earthquake engineering was already on the papers at the end of the 17th century, thanks to two persons like Robert Hooke and Isaac Newton. Again, it's very interesting to read about the fact that they were strong enemies. Isaac Newton was the official scientist writing in Latin. Robert Hooke was writing in English, which was kind of an insult for a scientist at that time, maybe with some reason, without reference to today, of course, where we use all English as the common barbarian dialect to exchange basic information. But it was all there in the sense that if you see this equation here, mass time acceleration equal stiffness times displacement, this is the force that derives from Robert Hooke, and the rest is coming from the equations by Isaac Newton. But the real moment in which this kind of approach became an approach applied to structures has possibly been the aftermath of the Messina earthquake. This point has already been raised in these days by other colleagues talking from this point. I like to underline at least one name, Arturo Danusso, who was a professor here for a certain time of his life. But look at this translation of the key sentences of one of the points of this report. Force is proportional to masses. Finally, Newton is there. How to find acceleration? Because if you want to calculate a force, you need also the acceleration. And if you don't have accelerometer, what do you do? Well, you apply back analysis. You look at buildings that have collapsed and buildings that have resisted, calculate the strength, divide by the mass, and you find bracketing acceleration. But then also, they were writing that there should be a greater tolerance with respect to the limits normally adopted as safety level. And this could be reached undervaluing the horizontal seismic forces, reducing them to around 1/3. So this was the first force reduction factor. And when the force comes out to be 0.1 G or 0.12 G, in their vision, this was 1/3 of the force that they were guessing that had happened to the structure. Clearly, this was something that was very advanced, but remained probably used, or maybe not even used, in a very small fraction of the world. So I would like to point out other names and other times. The next name that I want to point out is George Hausner. George Hausner, for me, was another prophet. You know that at the time of El Centro in 1940, he was a PhD student, or actually recently graduated, in the sense that these plots are not referring to the El Centro earthquake, but they refer to the first recording, the 1933 Long Beach earthquake. And you can see that here it was already clear some sort of displacement spectrum, and here some sort of acceleration spectrum. The concept of spectra and of their use was then perfectionated by many people. Few names have been mentioned by Jack Mele a couple of days ago. But I have always been fascinated by the fact that Nathan Newmark and a large number of other researchers arrived to propose this kind of tripartite spectrum, in which in one side you have constant acceleration, fine, I can understand physical reasons. On another part you have constant displacement, fine, I can find physical reason. But the fact that in between they assume to have constant velocity has no physical reason at all, and it is just a matter of beauty. You know, acceleration, velocity, displacement. It's not too far away from reality, but it comes from intuition. It comes from very few data. It comes from the use of brain, and maybe it's wrong, but it's elegant, which is already something. In this context, after the San Fernando earthquake, it was the time when it came out, the idea of somehow considering ductility as a key factor, and it was the time when another form of force reduction factor came out. And in some cases, again, equating energy, which is another principle that have very little physical fundament, but is nice. And therefore, the first inelastic spectra were produced. Of all this evolution, the most important point of all for earthquake engineering was, without any doubt, in my opinion, the development of capacity design. It has been made clear recently in a paper by Michael Fardis that the first sentence clearly expressing the fundamental of capacity design was written by Mette Sosen, and this is the sentence that I am reporting here in this slide. But it is also well recognized that without the capacity of application of people like Tom Polay, this would have been remaining a sentence in a report. So I think that we should recognize this different contribution to something. One thing is to have the idea, another thing is to be able to transform the idea in practical applications. In this context, I think that after the earthquakes in there is a mistake there, 1989, Loma Prieta, then 1994, Northridge, and 1995, Kobe, people started considering that there were aspects that were not working properly. And I don't think I'm biased by the fact that he has been for some 30 years one of my best friends. I believe that Nigel Priestley was fundamental in clearly stating this kind of difficulties. One point is that there are many structures in which it is impossible to have a uniform ductility. So if you use a unique force reduction factor, you cannot protect in the same way different elements of a structure. This is clear for coupled shear walls, it's clear for columns or bridges with a different height, it's clear for marginal wharfs with columns and piles that have a different, are embedded in a different way in the soil. So this is one point. A second point is the recognition that in structure there could be dual systems, dual path to resist the force and displacement demand. For example, in the response of a bridge, you could have the contribution of the deck and the contribution of the pier, but only the piers will go into the nonlinear range. So if you apply a unique force reduction factor to both, you are assuming that the deck is also going into the nonlinear range, while this is not true. So the deck will contribute more than what you are expecting. And more than anything else, the proportionality between strength and stiffness that makes it essentially impossible to estimate at the beginning of a design process what is the period of vibration of a structure, in the sense that you do not know yet the strength because you are starting the design. And when you calculate the strength, you should at least revise your assumption on stiffness, which is the crucial parameter to define the period of vibration. It is in this context that the displacement-based design approach has been developed. I apologize because this is not the last version of my presentation. There are a couple of slides missing. Anyway, in the slides missing, I was recognizing that there had been early intuitions about possible aspects to be considered. One was certainly the approach by Jacobsen that wrote down an equivalence between energy dissipation and equivalent damping. Another one were the approach by Sozen and Shibata and Sozen and Gulken that were proposing to have a substitute structure that was using some sort of second stiffness. And therefore, instead of using a force reduction factor, you might already start considering and seeing and thinking that you could use a second stiffness combined with an energy dissipation associated to damping. But all this remained in papers. I consider this similar to the same story that I was telling earlier. It was only thanks to Nigel Priestley that this kind of intuition have been transformed into a complete method to design structures that today is applied by thousands of people specifically to design. So a structure becomes a single degree of freedom model. It is characterized by a second stiffness. This second stiffness is associated to a certain level of energy dissipation. This energy dissipation is associated to a damping value, and then the damping value is used to correct the displacement spectrum, and then entering the spectrum with a displacement, you can obtain a period of vibration that multiplied by a stiffness gives you a strength. The Jacobsen approach has been used in many ways to find equivalence, find equations, formulations to calculate some displacement reduction factor. I like to underline that as long as you have some ductility, say ductility 2, then all equations are going to use some correction which is in the range of 0.6, or most equations. So if you are using this for preliminary design, there is not any reason to go in a more detailed calculation. This is very convenient because it means that when you are starting the design, you could assume that the displacement demand will be in the range of, say, 0.6 times the elastic displacement demand, provided that you have at least some energy dissipation capacity in the structure, which means some ductility. In this context, it is marvelous, it is incredible, in my opinion, how many difficult problems can fit. For example, second-order effects. If you want to have something which is going to a certain displacement and you calculate a certain stiffness applying the procedure, and your structure is not a structure that goes up like this but comes down because of second-order effects, then you can easily calculate what is the increment in the strength that you should use to go to this point. So instead of using correction made by the ratio between the second and the first order moment and so on and so forth, you can calculate something which is more sound. Or if you want to take into consideration higher modes in design, not neglect them and then go for some analysis to find out what to do, you can apply your correction factor only to one mode, and then for the other mode to use the full response. It's something similar to the dual path that I was talking about earlier. And this is an approach that has been developed by Nigel Priestley, but if there should be here my final slides, here you would have been reading also the name of Joseph Heibler, which is a German professor that had not much to do with earthquake engineering, but was suggesting this kind of approach in the context of, in a different context, but anyway, to consider higher modes. And the third point that I would like to underline is the problem of torsional effects that, again, normally are not considered at preliminary design phase because people do not know what to do. But thanks to Tom Poley first, who started noting that if you are in earthquake engineering, in seismic design, you are assuming that all the elements are going to enter the nonlinear range. And therefore, the eccentricity is with reference to the point of strength, not to the point of stiffness. And they are very different points, one with respect to the others. But in a context of displacement-based design, you can simply use the displacement that you have available after having considered a certain rotation due to the torsional response. Bridges, you could consider a displaced shape in bridges, and you can, again, go for a single degree of freedom model. Or, until I started 20 years ago applying this kind of design procedures, the way applied, the way to design an isolated structure was very crude and very with no sense, no physical sense. While in a displacement design approach, you can take into consideration the fact that the upper structure could be more or less flexible and consider the displacement of this structure depending on its capacity without going into the nonlinear range, so maybe 80% of the yield displacements or something like that. And this also gives you a lot of possibility when you're dealing with apparently more complex problems like rocking structures that, after all, it is a combination of some sort of base isolation and some sort of P-delta effect, because the more you go displaced, the more the structure will decrease its capacity. So now let me shift again to something else that maybe could surprise some of you. I want to talk briefly about seismic action for engineers. And again, I apologize for the possibly too many words, but here are a few sentences in one fundamental paper by Alain Cornell, another name that should remain in our story of people. And just look at how many times he's using the word engineers. One of the problems we are facing is the fact that engineers and seismologists are really not working together and talking to each other. But if I should make a choice, not because I am an engineer, but because I understand that it's the structures that has to be constructed. So what Alain Cornell was saying is we should have some way of applying a probabilistic seismic hazard approach. But at the end, since it's a problem of risk, the main aspects is related to structure. So is it on that side? From a certain point of view, the definition of input should serve the structure and not the opposite way. And certainly they cannot be looked at in a separate way. I spent some time in reading a lot of papers related to these subjects. First of all, a paper that I received in printing this evening by a friend, which is here in the first row. And because of this, I have gone back to old papers. And another person that I like to remind in this room is Charles Richter. Charles Richter was a fascinating person. By the way, there is a very interesting book that tells the story of his life. I think the title is Measure of an Earthquake, Measure of a Man, or something like that. It was a bit crazy. He was an astronomist, you know, a failed astronomist, actually. And that's the reason why we use the word magnitude for the energy released by an earthquake, because he wanted to use the scale of use for the stars in the opposite way. But anyway, it is fascinating to read what he was writing in 35 and then in the 40s, saying it would be so nice to have a scale based on energy, on something that is measurable. And then noting that the ratio of maximum amplitudes of two given shocks registered by different instruments at equal epicentral distances is approximately constant. And on this, you started basing his scale. Noting that there was an enormous difference in energy release, and this was the reason why I used the logarithmic scale. But what is again, for me, fascinating is to note that he was stating that to have an absolute scale would have been great, but he had not a clue about the real energy released by earthquake. Again, in my final slide here, there was another name, Jeffries, who was the first one who tried to measure the energy released in earthquake. And look at this equation, which was the original equation used by Richter, where you are not used to see a 2 factor here. If you use a 2 factor here, it means that the difference in energy release at 1 unit of distance in magnitude is 10 to the square, so it is 10 times. And 2 point in magnitude, according to this equation, is 10,000, is 10 to the 4th. So it's 10,000, but this was clearly modified and with something, again, very fundamental, when Kanamori and Anderson actually wrote out something that today sounds to us very obvious. But this is what happens to great ideas. They simply stated that the energy here, M0 is an energy, can be calculated as a function of the fault area that has been inducing the earthquake, the fault slip, and the shear modulus of the soil. But the shear modulus is more or less constant. So it means simply that the energy depends on the size and on the displacement. And what they did was to reuse the equation proposed by Richter, and the 2 here became 1.5. So it means that now the difference in energy released at 2 points in the scale is 1,000 not 10,000. And this is very, very fascinating to me. And here I wrote down this table just to say that you could, when you have some clear example, like in the Northern Anatolian Fault, you can correlate easily the return period to the magnitude. We mean to correlate it to the energy released and so on, and to the dislocation of the fault and to this broken area of the fault, and therefore to the length of the broken fault. This is not something special, but it's something that gives me some confidence in figures and in what they would mean. Change again, but still on seismic action for engineers, but local soil effects. This is an old figure in a paper by Idris and Seed, where, based on a very limited number of records, actually you see 28 records on rock and 15 records on soft to medium clay and whatever, they noted that the spectral shape on rock tend to be extended but decreases in value. If I look at spectral shapes in the Eurocode up to years ago, up to a certain date, they were closer to this representation. Then they moved to something like this, where you see that the soft soil, instead of coming down, goes up. The reason was that these were derived, and this is not the present set of spectra, but the reason was that people started doing numerical analysis. They did not simulate the failure of soil, because if soil reaches some source of yielding, some source of plasticity, the displacement increases, but the acceleration cannot increase anymore. So this is essentially the product of some inappropriate modeling of the soil. Going ahead along these lines, you probably know that there is no reason why we're using a 10% probability in 50 years or 500 years return period or so, but this was just written the first time in a report by Algermissen and Perkins, where they were saying, let's, for example, assume that we are using 10% in 50 years. But anyway, here I go back to the representation I was using earlier, and particularly to this representation, so spectral acceleration versus spectral displacement, to note that there is an area here that we, as engineers, we are not interested in at all. There is an area here where we are not interested in at all. So we only want to know this part here, and the shape of this part here. This is what we need for design. And to do that, in recent times, there have been a few considerations. One is a consideration in a paper by Boer in 2010, where he started noting that, well, when we design, we are not using the northwest, the north-south and the east-west spectral shape. We want to use one spectrum. And this spectrum, at the end, what we want is something that represents the vector, which is the maximum value in any instant. So this vector is never in the same direction, because the combination of spectral acceleration and spectral displacement are changing. And if you do something like that, you obtain different spectra. And the other point, actually, this is I've not put any name because there is no reason, is that the peak in average spectra are very different from the average of peaks. Take this as an example. If you take the blue spectrum and the red spectrum, and you take this point as a peak and this point as a peak, and you come out with the average spectrum, the black and the blue, the red is the average spectrum, then the peak in the average spectrum is here. But if you take the peak here and you take the peak here, then the average is here. So you have a completely different thing. What are we looking for? For the peak in average spectral shapes or for the average of the peak? You obtain completely different shapes. these are plots obtained from 6,866 records. And if you compare the blue plots with the red plots, you see that this red here is close to the blue, this blue here, but this red is the average, and this blue is +1 sigma. And this is the average, this is the +1 sigma, and this is +2 sigmas. So you obtain something very different in terms of demand. And of course, the shape of the middle part is changing. I don't want to spend too much time, but if you go ahead and you take results considering the different kind of soil, you will find out that if you take a spectrum, for example, take this one, magnitude 5.5 with 5 kilometers, from rock to soft soil, you go up. If you take this, you go up in a different way. So what I'm trying to say, here is magnitude 5.5 at 45 kilometers. What I'm trying to say that here, this black plot here implies that there has been some nonlinear response in the soil. Why? Because you are close to the epicenter and therefore the action is stronger. So the amplification of spectral shape depends on the level of the action. Continuing along this line, I was talking earlier about the correction due to the Jacobsen approach, and we have always been correcting spectra and going down this way, which is clearly a mistake. We are reducing displacement, not acceleration, and this was done in the old time by intuition, then modified because of too many numbers and too many calculations. But if you take this correction and not this correction, you are not modifying this part here. So you go from an elastic spectrum like this to something like this to something like this. You are correcting significantly this point, but not that point. And based on this consideration, we could go back to some sort of definition of, say, in inverted commas, non-seismic zones. Why? Because would anyone object on the fact that any structure should be able, for example, to take a 10 millimeters displacement? Okay, so if we can define areas where there is not more than 10 millimeters displacement demand, there is little reason to consider seismic action. Now, I see that I will never be able to finish this talk, so I will skip the second part, only telling you what is referring to. But I want to devote 5 minutes to the evolution of loss-based design. I am going back to George Hausner. I believe that his report, published after the Loma Prieta earthquake, the title was Competing Against Time, where he was stating earthquakes will occur whether they are catastrophe or not, depends on our action. In that report, he was just putting the fundamental ideas of performance-based design. These figures by Ron Hamburger has been shown several times, for example, by Jack Mellett 2 days ago. But I would like to move to something like this. This deserves 1 minute of attention. If I plot the annual probability of exceedance, which is 1 over the return period. So if I'm very low here, it means maybe that this is 1,000 years return period. Maybe up here is 500 years return period. Maybe here is 200 years return period, and so on. And here I plot the expected loss divided by the cost of reconstruction. What does it mean? It means that if I have a 1,000 year return period, here I am designing for strength. So for that 1,000 year return period, I have 100% losses. Okay? Up here, this point here has something to do with what Julian Bommer was calling magnitude mean in the opening ceremony in the first lecture of this conference. So the fact that here you consider a 10 years return period or a 20 years return period again, but it's the threshold of the minimum loss that you want to consider. Now, the definition of an expected annual loss is the area which is below each one of these curves. So it's the integral of the annual probability of exceedance over the expected annual loss in all this plot, which has 2 limits. Now, if you look at figures that we're using today, we are probably in the line of these green curves or something like that, in the sense that we are then designing for a third point that we could call a control point. Maybe it could be 20% loss for 100 return period earthquake, ground motion. So if we want to go down and design for less loss, it is not very important to reduce this point. What is more important is to take the curve down. And I will come back to this soon, but let me clearly state 2 points. One, this expected donor loss is essentially a strong function of that control point and not a function of the probability of collapse or of the ground motion that you consider at the onset of damage. Second, this expected donor loss depends strongly on indirect losses. So we have to do calculations including indirect losses. Finally, let me spend a few words on how we could design structure. If we want to reduce the expected donor loss, we have to consider frequent event. For example, I'm here plotting as an example, I am saying, the response spectrum of magnitude 4.5 kilometers and the response spectrum of magnitude 6.5 at 40 kilometers. Assume that these are controlling events for a 100 return period ground motion. Then you want to set a limit in displacement, so you cannot go lower than this red arrow, because otherwise you have too much displacement. But you also want to fix a limit in floor acceleration, because there are elements sensitive to acceleration. You don't want to go in this direction, to the left of this black arrow. So you know, you will find out that you have to design in this angle, not outside this angle. Now, if you add another spectral shape, a spectral shape, for example, with a magnitude 6.5 at 5 kilometers, and of course this is much larger, much more demanding than the two spectral shapes that you were using first, you are reducing damage and staying in this angle, but then here you need displacement capacity to avoid collapse. So you are respecting two different principles. One, limit the damage. One, avoid collapse, limit the number of casualties and protect the human life. If you go, and I'm close to finish, to the problem of strategic structure, to a hospital or something like that, you don't want to change the probability of collapse. You want to take this point here and to take it down here. You want to reduce the collapse. You want to have the structure working after an earthquake. Therefore, your design should be completely different. You have a limit in displacement, which is here, so you have to stay on this side. You have a limit of acceleration, which is here, so you have to stay on this side. Of course, there is no solution. But for example, if you use base isolation and this spectral shape is reduced to this spectral shape as a floor response spectrum, then you can design for this green line what? The structure, the construction, which is on top of the base isolation level. So I'm trying to use the base isolation level as a filter, as a modification of the input ground motion, and then I want to design the structure for that ground motion. And in this way, I will take care of non-structural elements and so on. At this point, I was going to tell you about a completely different section of the monographs where I had fun in writing some 100 pages of end calculations to show that what I was trying to describe could be done with a piece of paper and a pen, and you could do all these sort of things. I have no time to do that, so you see all these drawings have been handwriting of mine. I had a lot of fun with this, but I have no time because otherwise Helen will complain with me. So I leave you with a monograph to read if you want to know what were the choice of modifying an abutment or to design a shear key or to be able to calculate by hands the force displacement curves of complex piers, just concentrating the reinforcement and the concrete in different points, to come to a final sentence, which is the sentence that was used to another good friend of mine. So the name is not there, but I tell you the name. The name is Michael Collins. He's rather sick now, but he was often using this and indicating this as one of the fundamental law of structural engineering. I close my presentation.
You stand in the middle. Okay. He's the master. Okay. Well, thank you so much. Don't stay here, sir. I wish I could receive questions from the audience, but in the interest of time today, no. But whoever has questions, read his monograph first. This solves 90% of your time. But anyway, Mr. Master, thank you so much for your very informative lecture today. And this completes today's Master's event. Thank you so much for joining all of us today. Thank you so much. But